Yes, indeed. The 11 o'clock train is pulling out of the station. And let me go to speaker view. And this is these are the notes from yesterday. We talked about amplitude, period, frequency, and shift, which we didn't quite call a phase shift. But yeah, so we were graphing here an example of 3/4 cosine 2x plus 2 pi over 3. And all that stuff we learned about transformations on functions comes to bear. The kind of bear you see in the woods. No, there's another kind. So we had this table of values, and that got us only halfway through, right? But we do see some symmetries in here. Let's see. Do I have, what kind of pencil action do I have here today? I should have a mechanical pencil, would be nice, huh? Well, I've got this old-fashioned pencil. And pretty sure I had a mechanical pencil. It's in my shirt pocket or something. This is a mechanical pencil. It's 0.5. I find that to be a little bit small. Pretty sure I had a 0.7 here somewhere, but 0.7 what? Like millimeters or something? Does it say anything? Yeah, millimeters. That's fine. 0.5 millimeter. Okay, so we're halfway around the circle. So what are the remaining places? Well, we had some confusion about that. I'm sorry. But yeah, so if you go by pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6 is pi. 7 pi over 6 is here. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. That's here. 11 pi over 6 would be here. And then the quarter, well, the eighth terms, I guess you would call that, right? So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. This is 5 pi over 4. And 6 pi over 4, 7 pi over 4 is here. And then 8 pi over 4 takes us back home again, right? So for the bottom half of the unit circle, we're going to have what, 0.7 pi over 6. And this is, a good way to sort of warm up here today, I think. Extend this table to complete. Okay. 4 pi over 3 is next. It's a little disorienting the way these fractions reduce, isn't it, right? That's why I try to stick to like over 6 or over 12 and then reduce, right? So this is what, 16 pi over 12 or 8 pi over 6, right? And 4 pi over 3. And then we have 3 pi over 2 is the South Pole, Penguin Land. 5 pi over 3, 7 pi over 4, 11 pi over 6, and then we're back home at 2 pi, right? So what are our function values at these points? We've got f of x and g of x, and then the sum of f of x and g of x. And we saw a pattern in f of x, right? Was I forgetting to multiply by 2 here? F of x is twice cosine of x, right? 3 pi over 4, yeah, so this should be, I don't know, I was a little bit out of sorts yesterday. So this should be, yeah, so twice negative 1/2 is negative 1. Twice negative square root of 2 over 2 is negative square root of 2, right? And twice negative square root of 3 over 2, right? Because f of x has this factor of 2, which I somehow was forgetting about here. And then at pi, cosine of pi is -1, so twice that is going to be -2. Mercy. Okay. So now these are the sine values, and I think if the input is 2 pi over 3, and we're doubling the input for g of x, then that's going to be 4 pi over 3, which we look up on the circle, and we see that's here, and the sine value there is indeed negative square root 3 over 2, right? So this is a good value here. So that's that one. So how about 3 pi over 4? Well, oh yeah, we just did that one, right? And 3 pi over -1. Okay, so this one is good. Although this is not good. Mercy. So this should be negative square root of 2 minus 1, which is indeed approximately, oh, well, square root of 2 is 1.4, so negative 2.4 approximately. I think this is correct. So now this one is going to be, I just kind of fell into a wrong groove. Do you ever happen that ever happened to you? How are we doing? I should get the chat visible here so I can see if you want to comment on the bad groove. Yeah, so I think these two values are now correct. Should we double check? Cosine of 5 pi over 6, where are we? 5 pi over 6, we're here. And cosine there is negative square root of 3 over 2. If you double that, you get negative square root of 3, which maybe I'll make that larger. This is negative square root of 3. And doubling 5 pi over 6, we get 5 pi over 3, where we see the y value is sine, right? And that's going to be negative square root of 3 over 2. So this is approximately negative 1.7, approximately negative 0.9, 0.866. I'm going to say 0.9 and 1.7 is 2.6. That's going to be negative 2.6 approximately. All right. And at pi, cosine of pi is -1. Twice that is -2. Twice pi is 2 pi. And so sine of 2 pi is 0. And so these add up to -2. All right, we're adding. And should we check? I think I have a GeoGebra thing here. Okay. File, open, and I think it's called waveform. Look at that. And are these in fact what we expect them to be? Yeah, we should see symmetry, right? Yeah, so if we look back at our table, do we see that symmetry in the table? Yeah, this is 2, root 3, root 2, 1, 0, and then back down the same way, right? -1, negative root 2, negative root 3, -2. So this one is oscillating twice as fast, right? So we got 0, root 3 over 2, 1, root 3 over 2, 0. And then on the negative side, negative root 3 over 2, -1, negative root 3 over 2, 0. Okay, so let's keep going. And 7 pi over 6, cosine of 7 pi over 6, that's here. That's going to be negative root 3 over 2, right? Dial that up there. and the x coordinate right there is negative root 3 over 2. We're going to double that and get negative root 3. Okay. Well, I think we're just going to, wind our way back up the same way we went down, right? So negative 2 is the minimum. I'm going to go negative root 3, negative root 2, negative 1, 0, 1, root 2, root 3, and 2. All right, just not overdo it. Let's then for the g function, we're going to double the input and then compute the sign, right? So if the input is 7 pi over 6, 7 pi over 3, where's 7 pi over 3? Well, that's more than 2 pi, right? So it's coterminal with pi over 3, right? 6 pi over 3 is 2 pi. So 7 pi over 3 is pi over 3 more than that, which will put us up here where the y coordinate is root 3 over 2. And do we see a pattern there? Yeah, we went down, now we're going to 0. We're going to repeat all these values, right? So we can just use the symmetry and say, yeah, we're going to reach our max, we're going to head back down, be at 0, right? 3 pi over 2, twice that is 3 pi, sine of 3 pi. 3 pi is coterminal with pi, right? Where y is 0. And then we'll go negative root 3 over 2, negative 1, back up, negative root 3 over 2, back to 0. And so what are the sums? Well, this is negative root 3 plus root 3 over 2. All right. So up here we had root 3 plus root 3 over 2. Now it's negative root 3 plus root 3 over 2, right? So they're a little bit out of, so there's negative 1.7. We approximate, let's approximate that. Negative root 3 plus root 3 over 2. That's approximately negative 1.732 plus 0.87, 0.866. I'm going to round to the nearest hundredth there. And we subtract the smaller from the larger and get 16 minus 8 is 8. And so it's going to be negative 0.85. Okay. So that's this approximate value. Okay. And then 1 minus negative 1.44, that's going to be negative 0.4 roughly. And negative 1 plus 0.866 is going to be negative 0.13, shall we say? 0 plus 0 is 0. Then this is again, this is the opposite of that, right? So it's going to be a positive 0.13. It's going to be a positive 0.4. It's going to be a positive 0.85. And then a positive 2. Should we check that those values are correct in GeoGebra? Plot those points. So far we showed the upper half of the unit circle. Now we're going to do the lower half of the unit circle. And that gives us, so our function h is f plus g, right? And so we can plot, let's say 7 pi over 6 and then comma h of 7 pi over 6. There it is, okay, that point. And then 5 pi over 4. 5 pi over 4, h of 5 pi over 4. over 4. Okay, there's that point. You see it? And then 4 pi over 3. Okay, so we say 4 pi over 3, comma, h of 4 pi over 3 is that point. And then I'm going to have 3 pi over 2, 0, right? That's a 0. So 3 pi over 2, comma, 0. And then all these other points are going to be the opposites of the ones we just plugged in, right? But let's go ahead and enter them in. So 5 pi over 3 is the next input. 5 pi over 3, comma, h of 5 pi over 3. Yeah. And then 7 pi over 4. So 7 pi over 4, comma, h of 7 pi over 4. There's that point. We're almost home, folks. So 11 pi over 6, almost 2 pi, right? Comma, h of 11 pi over 6. That point. And I guess we've got 2 pi, comma, 2. Doesn't want to plot that point. I think that should be that maximum point, right? Oh, huh. Oh, this is not a maximum. Oh yeah, it's not, right? Yeah, we're a little bit out of phase, right? So I think, in fact, we'd have to go to 13 pi over 6. So another pi over 6. Right, so I'm going to say 13 pi over 6, just a little bit beyond 2 pi, right? Because the peak is not, we don't start at the peak, right? So we've kind of completed one waveform, but if we just want to pick up that next peak, we'd go to 13 pi over 6, comma, h of 13 pi over 6. And there it is, right? And yeah, so kind of an interesting waveform. Um, so let's see a little bit more about this. So this comes under the heading of additive synthesis, right? So if we go to our search engine here and we say additive synthesis sinusoid applet, or what do you call it when you have a little well, I'll search for that. So there's a Wikipedia entry. Yeah, so this is like electronics. It's not exactly what I want. Sound on sound. Yeah, I'm using an ad blocker, you bet. Okay, so this is kind of getting McGill University. That's in Montreal, I believe. Okay, that's not what I want either. I want a little applet. Maybe if I put applet here. Always then it'll give you something for your phone. I don't really want waveform generator. Oh, we were kind of looking at this before, right? So here's your basic sine wave, right? And if I press square wave, what am I looking at here? I've got something that kind of looks like it's, almost constant and then drops to its opposite down here, almost constant. And these are the various frequencies and their amplitudes that are being added together to produce this this waveform here. It's not really great. Music and computers. Yeah, that's not what I want either. Yeah, that's something where I can. So, okay, well, that's fine. We don't have to find something perfect for that purpose. Shall we look at the 5.3 homework? It's taken a while. Okay, there we go. Oh, okay, so they've got trigonometric graphs. Did we watch this? Maybe we'll just mute that because, oh, I see. So they've got, yeah, trigonometric graphs. What are they good for? Who uses them? Why do I have to do them? When you have a repeating pattern, you can describe it using trigonometric graphs. Am I like going fast or something? Oh, playback speed is normal. That's all right. Yeah, so you get spring mass systems, phases of the moon, tsunamis, um, and of course, music. Waves have height and depth, amplitude, length, each wave, that's the period. How often, frequency, how many oscillations per second. So amplitude indicates how much energy is in a wave. There's a low energy is low amplitude, high energy is high amplitude. So the amplitude is multiplying the output. Um, now for an animation of amplitude. Okay, so you can see as you go around the unit circle and you lay out your y coordinate um, uh, corresponding to a horizontal input. Okay, so you can change the amplitude with the slider. Yeah, you could do that in GeoGebra, right? This may well be a GeoGebra application here. Period is the time taken per cycle. And so that multiplies the input, right? Okay, well, you can watch the rest of that on your own. We kind of been over that, right? So what's the amplitude here? Well, clearly the output is being multiplied by 4, and the period, well, so we want 7 times x to go between 0 and 2 pi, right? For the input to the sine function should range between 0 and 2 pi. What does that mean about x? Well, x would range between 0 and 2 pi over 7 if you have this factor of 7 there, right? So 2 pi over 7 is the period. Is that correct? Yep, that's right. So what is the amplitude here? Well, 8, right? You wouldn't say -8 because amplitude should be positive. So what does the negative do? That reflects across the x-axis, right? All the y's become their opposites on the other side. What is the period? Well, that's determined by this little multiplier here, right? It is not equal to that, but 2 pi over that is the period, right? So 2 pi over 3 is the period of oscillation here. And what is the phase? Oh, they're calling it a phase shift. So what's the horizontal shift? What's the smallest horizontal shift that will move your equilibrium point? Oh, this is a cosine function, right? Let me go ahead and graph this thing, and then we'll talk about what the phase shift might mean here, right? So I'm going to get my pencil and paper going. And should we try the mechanical pencil? It's a little bit different. Okay, so I've got then the function y, the dependent variable y, is determined by this formula, 8 times the cosine of 3 times x plus pi over 3. All right, and so we want the input to range between 0 and 2 pi. So we can say, here's the input, 3 times x plus pi over 3. That should go between 0 and 2 pi for one complete wavelength, right? That's the input to this sinusoid cosine. This is a 3 here. Okay. So solve for x, this compound inequality. So divide each member by 3, you get x plus pi over 3 greater than or equal to 0. 0 divided by 3 is still 0. 2 pi divided by 3. And then subtract pi over 3 from each member. And 2 pi over 3 minus pi over 3 is pi over 3. Okay. What's the distance from negative pi over 3 to pi over 3? Well, 2 pi over 3, which is our period, right? So this is one complete period where we start, well, we're actually going to start on a trough because of this negative sign here, right? But let's go ahead and make a table of values. And we'll start at negative pi over 3, why not? Where we'll see that the input is 0, right? And cosine of 0 is 1, negative 8 times 1 is negative 8. Okay, so the wavelength is the wavelength or period. That means the same thing, right? Wavelength equals period here equals 2 pi over 3, right? So what's a quarter wavelength? Well, that's going to be pi over 6. All right, so that's what I want my increment to be in the table, so I can pick up the key values, right? So when I add pi over 6 to negative 2 pi over 6, I get negative pi over 6. And then I'm going to be at equilibrium. Does that work? Yeah, negative pi over 6 plus pi over 3. It's going to be pi over 6. 3 times pi over 6 is pi over 2. Cosine of pi over 2 is 0. Anything times 0 is 0. All right, so the next increment will take me to 0. Cosine of pi is negative 1, so that'll be positive 8. Another pi over 6 will take me to 0 again. And then another pi over 6 will take me to pi over 3 as the input and back to negative 8. So that's one cycle through our function, starting at a trough and ending at a trough. So if you wanted to start at a peak and end at a peak, you could do a couple more of these, right? So pi over 2 would be pi over 3 plus pi over 6 is pi over 2. A little bit of arithmetic there. Another pi over 6. Oh, this is 3 pi over 6 plus pi over 6 is 4 pi over 6 or 2 pi over 3, right? So if I were to plot these things, what would it look like? Let's do it up here. I'm going to say, yeah, I can say I've got hash marks, perfectly evenly spaced hash marks. And let's see, on the vertical, I want to oscillate between 8 and negative 8, right? So I can say, well, I want these to be evenly spaced, right? So let's say here's 8 on the y-axis. This is the x-axis. Here's negative 8. So what's this? Well, let's say that's negative pi over 3. So this is our starting point at negative 8. And then we'll be at 0 at negative pi over 6. Be at 8 at 0. This is going to be pi over 6 then, right? We'll be back at 0. We're at pi over 3. We're at negative 8 again. This is pi over 2. Yeah, those are perfectly evenly spaced. And this is then 2 pi over 3, right? I will be back up at 8. So the curve is going to look like this, right? Okay. That look convincing? It should be smooth. line there, right? So that's a cosine function. So, so if you just looked at the part that starts at a peak and ends at the peak, you'd say, well, there's no shift at all for that. And I could write this as positive 8 times cosine of 3x. Same thing, huh? Right? It's got a wavelength of 2 pi over 3. So as we go from 0 to 2 pi over 3, we start at a peak. Cosine of 0 is 1 times 8 is 8. And at 2 pi over 3, well, 3 times that is 2 pi. Cosine of 2 pi is 1 again, right? And 8 times 1 is 8 again. So that's one complete oscillation of our cosine curve. So what would you say the phase shift of that is? Well, I'd say the phase shift is 0, right? For cosine is 0 because that's the smallest shift that will start me at a peak, whereas that's where the cosine curve starts. But maybe this is a sine curve, right? So the phase shift for and now this can be written as a sine curve, right? So what would the phase shift be? It started at equilibrium and ended equilibrium. And so another way of writing this thing is 8 times the sine of 3 times, whoops, delicate, 3 times x minus pi over 6. Darn it. So that is yet another way to write this function, right? So there's a lot of different ways you can write this function. If I write it this way, then I'd say, well, as a sine curve, the phase shift is pi over 6. Oh, sorry, it should be a plus, right? So pi over 6 to the left, or it would be negative pi over 6. So I'm a little confused, right? And I think this phase shift is a very slippery thing. It's generally poorly defined. I'm sorry to say it, but I just have to admit it. So I think, you know, if you whatever business you're working for, you have to ask them, what is your definition for phase shift, and then use that, right? So if you're just thinking, let's go back to the problem. If you're just thinking, what is the horizontal shift of this function? You might say, well, pi over 3 to the left, right? Because x has been replaced by x plus pi over 3. And let's see if that's acceptable to them. I'll bet you that's kind of what they expect here, right? Yeah. But what if I put a 0 here? Would they accept that? No, they don't like that because that's where the cosine starts at a peak. Whatever, right? How about negative pi over 6, which I think is also a reasonable answer if you're thinking of this as, you know, a sine curve. But no, they don't want that either. They just want what is the horizontal shift of this function, which has a negative in front, which, yeah, I wouldn't write this function that way. I'm sure that's confusing, right? And I don't want to make any bones about it. The screen is blurry. Is that true? Let me go back. Maybe can I make it a little brighter? And maybe focus. That's as good as we're going to get. Maybe if I move this thing a little bit to the side. Yeah. I know it's not great imagery. All right. So, yeah, there can be some confusion. You know, have you been to the Date Festival? Walked into the House of Mirrors? It's kind of like that, right? It's like, what is that the real thing, or is that like a reflection of a reflection of a reflection of the real thing? What's the real thing? Maybe there is no real thing. Yeah. All right. Let's move on, shall we? How about question 4 here? Let y equal this thing. What is the amplitude? Well, that's the square root of 18. I'm trying to make it tricky, but it's just whatever is multiplying the output, right? Oh, the square root of 18, I think we want to say 3 times the square root of 2, right? Since 18 is 9 times 2. And that's a simplified version of the square root of 18, isn't it? What is the period? Well, the multiplier of the input, x, is 2 pi, and so 2 pi over 2 pi, right? Which is 1. So this has a period of 1. What is the phase shift? Well, that's a little bit tricky, so let's do some pencil and paper on that. So if you've got y equals, I'm going to write 3 times the square, 3 times the square root of 2 sine of 2 pi x plus 9 times e to the negative 4. What the heck is e? Well, it's a little bit anachronistic. In fact, in chapter 4, they define e, and we're in chapter 5. So the authors of the text think, well, they know what e is. Well, let me just tell you, e is a special number like pi. It's approximately 2.71828. Okay, so it's just a number, right? And that number to the negative 4 power is going to be pretty small, right? So 9 times that pretty small number is still going to be pretty small. But we have to factor out a 2 pi in order to get the actual shift, right? So it's going to be 2 pi times x plus 9 e to the negative 4 over 2 pi. You see that? We just distribute the 2 pi. 2 pi times x is 2 pi x, and 2 pi times this, well, the 2 pi cancels, and you get 9 times, this looks like a g, doesn't it? It's a 9. So the phase shift is negative, right? Because x minus a negative 9 e to the negative 4 over 2 pi. Let's see if that's what they want here. So I get negative 9 e to the negative 4 divided by, in parentheses, 2 pi. Right? We kind of need the parentheses so that, otherwise the order of operation would say divide by 2 and then multiply the result by pi. And you can look at the pretty type and see it comes out the way we want it. And yeah, that's going to work. Okay. Questions about that, or just kind of move on, right? Trying to think of what room you mean. Oh, yeah, right. The House of Mirrors, right? Yeah. I guess we didn't have the Date Festival this year. So, all right. Probably just as well. I understand that the clowns are now, they have hung up their clown shoes or whatever. Anyway, so what do we, the amplitude here is 6, right? We always want the amplitude to be positive, and the period is 2 pi divided by a third, right? Which is 6 pi. Yeah. And here, the amplitude is 7. They're hot on these negatives, aren't they? The period is 2 pi, right? There's no multiplier, so it's just the natural period of 2 pi. And the phase shift is pi over 6. So that one's pretty straightforward. How about this one? Y equals negative 7 Okay, so again, the amplitude is +7. The period is 2 pi again. It's very similar to the other one, huh? And the phase shift is pi/4. Positive, right? Okay. Okay, well, so let's go to the text and see if there are more interesting problems in the text. I need to find where the text is. Okay, I think I can. Fit in the window like that. Okay, so a cosine curve with variable amplitude is the next topic here. And graph the functions y equals x squared, y equals -x squared, and the product x squared times cosine of 6 pi x on a common screen. So here, you know, the coefficient, the multiplier of the output, right? The coefficient of the cosine function is a variable, x squared. And so what that's going to mean is that it doesn't have a constant amplitude of oscillation, right? So we could just do this, right? We've got GeoGebra at the ready, do we not? And we can save this away and get a new file. I'm going to call this, well, so let's graph x squared. X squared. That's a parabola, familiar shape, right? And how about -x squared? Or in fact, let's not do that. Let's do -f(x). Same thing in a way, but if I just redefine f of x, then I don't have to redefine g of x. G of x is -f of x, right? And so h of x is going to be f of x times, and what do they want? Cosine of 6 pi x. Pi x. Yeah, that's it, all right. So what are we looking at here? Let's zoom in a little bit, right? So you can see that the peaks and troughs, instead of being constant values, are values on these curves, right? So when the cosine is 1, which happens here at, what is it, 1/3, 2 pi over 6 pi is 1/3, then you're on the curve y equals x squared. If the cosine is -1, then you're on the curve -x squared, right? Let's change this function and see how that changes things, right? So I'm going to say, yeah, let's make this 1/1 plus x squared, like that. Yeah? So you still see this sort of behavior, right? Where it's oscillating inside the envelope created by this multiplier function, where you have the function itself and then its opposite, right? Because the sine or the cosine oscillates between -1 and 1. So you oscillate between touching the opposite and the thing itself, right? So looks like that. We could stretch it out a little bit. Yeah. Okay. So what other goodies do they have for us here? Little discovery project with predator prey models. Yeah, we should maybe do one of those, right? I'll think about setting something for you to do. Cosine curve with variable amplitude, right? So that's just what we were talking about, right? Sine curve with decaying amplitude. Okay. So this is sort of a common situation. So maybe let's go back to GeoGebra and look at what happens if I change this to be, well, what's something that decays about 1 over x. Oh, cancel. I want to change this to simply 1. Well, this was sort of an example, right? You can see a decaying amplitude, right? Well, typically you have like an exponential function. So I'm going to say exponential. So this is e to the negative x. Oh, I don't want that. I want to change this to be e to the negative x. And this is like when you pluck a string, you know, it loses energy, right? It transfers heat to the air around it, loses energy that way. And so, you know, you pluck a string and eventually you don't hear it anymore. It dies off, right? So this is an example of what that would look like. Can we go through the problems again? I can't see them since it's blurry. Yeah, I think that may be the internets are causing it to be blurry. But basically all these problems were the same kind of, well, not all of them. Many of them were the same sort of thing. But let me, I can maybe make this more clear by zooming in, right? That probably helps, huh? So if we go to number 1, what do we have there? Oh, that was just to watch something. You click it when you're finished. So amplitude is 4, period is 2 pi over whatever coefficient of x is, right? Amplitude is 8, coefficient of x is 3, so 2 pi over 3. And here we got the phase shift wrong because I was experimenting. Originally we had negative pi over 3, right? Oh, have I already submitted this one? Maybe I've run out of submissions. Reattempt this question. Negative pi over 3 is what it's supposed to be, right? Right, that's just the horizontal shift, right? And so this is 3 root 2. I just simplified the square root of 18. There's a factor of 9, which is a perfect square there, which you can factor out. 9 times 2 is 18. So you factor out the square root of 9 is 3, right? The period is 2 pi over 2 pi. That's 1. And then we talked about how you have to factor out the 2 pi here. And so you get, yeah, negative 9 e to the negative 4 over 2 pi. And amplitude is 6. That's this multiplier here. Never mind the negative, right? And 2 pi divided by 1/3. Well, dividing by 1/3 is equivalent to multiplying by 3, right? So you get 6 pi. And amplitude is 7. Period is a natural 2 pi. Phase shift is simply pi over 6. And this one is very similar, right? So pi over 4. Yeah, sorry, I need to remember to make the image as large as possible so that we can see more betterly. Okay, how are we doing then? Back to the book. We have some exercises, right? So find the amplitude, period, horizontal shift of the function in graph 1 complete period. So let's do let's start at 41 and do those, right? Because here we also have a vertical shift, and we haven't really sort of added that to the mix yet, but it's just what you would expect, right? So I'm going to say here's 5.3 3 number, I still have, 5.3 number 41. And the instructions are, find the amplitude period horizontal shift of the function in graph 1 complete period. Okay, so in 41, the function is 1/2 minus 1/2 cosine of 2x minus pi over 3. So I mean, we might want to condition this expression a little bit before proceeding, right? The output of cosine is being multiplied by half. What does this half do? Well, that's just a vertical shift, right? So vertical shift up 1/2, right? That's what this does. And that means that y equals 1/2 is the equilibrium. That's what we oscillate around, right? Oscillate around your equilibrium. I suppose I could bring this in a little bit, make it bigger too. Maybe refocus. Okay. So then the amplitude is 1/2, right? This says that the period is pi, right? Two pi over 2 equals pi. And the phase shift, well, for that, let's rewrite this thing, right? I'm going to have 1/2 minus 1/2 cosine of, factor the 2 out of the input, right? And 2 times what is pi over 3? Well, pi over 6, right? Then you can see that explicitly that the horizontal shift is pi over 6 to the right. So that's your phase shift, right? So, so the wavelength is pi. So a quarter wavelength, and I like to compute this. Wavelength period, same thing, right? So a quarter wavelength is going to be pi over 4. So start at the phase shift and just keep adding pi over 4 for your table of values, right? So we want to make a graph of this thing, right? So I'm going to say here's x and y. And I'm going to start at pi over 6. Now this is a cosine function, but it's reflected through the axis, right? So when x is pi over 6, we're going to have cosine of 0 is 1. So we're at a trough, which is shifted up, right? So 1/2 minus 1/2 is 0. Then add a quarter wavelength. What's pi over 6 plus pi over 4? Now the common denominator is 12. So 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. That's our next input. And if we subtract pi over 6 from 5 pi over 12, well, that's 3 pi over 12, which is pi over 4. Twice pi over 4 is pi over 2. Well, it's just what you expect, right? Cosine of pi over 2 is 0. So 1/2 of 0 is 0. 1/2 minus 0 is 1/2. So we're on the equilibrium, right? So we started at a trough. We rose up to the equilibrium. Another pi over 4 down the road is going to be 8 pi over 12, which is 2 pi over 3. Yeah, I did that in my head. Maybe I shouldn't. But this is the same as 8 pi over 12, which is 5 pi over 12 plus 3 pi over 12, right? And this is also 4 pi over 6. Take away pi over 6, you're at 3 pi over 6, which is pi over 2. Twice pi over 2 is pi. Cosine of pi is -1. So 1/2 minus -1/2 is 1. So we're now at the peak, which is 1 amplitude above the equilibrium. The amplitude is 1/2. So 1/2 above 1/2 is 1. Okay, so we need 2 more points. So this is 8 pi over 12. We're going to add 3 pi over 12 to that, right? And get 11 pi over 12, where we're back at equilibrium. I'm not even going to bother, plugging in, right? Because you can see what's going to happen here, right? Another 3 pi over 12 down the road gets us to 14 pi over 12, or 7 pi over 6, which is pi more than pi over 6, right? So that's 1 complete wavelength. We're back at a trough. So let's plot these points, shall we? And the action is all over in the first quadrant, right? So I'm going to emphasize the first quadrant. And let's see, we're oscillating with amplitude 1/2 around 1/2. So if I make this, well, here's 1/2, here's then 1. Oh no, that's wrong. Let's call this 1/2 and this 1. Don't mind that extra hash mark there. It's not perfectly evenly spaced. There, the magic of erasure. No, kind of. So this is the y-axis, right? And this is the x-axis. Now we need to scale our x-axis as well, right? So we want essentially 4 intervals, but we're going to start off 1, 2, 3. I think, can we fit that in there? Yeah, let's do that. So, yeah. Yeah. So we want to start at pi over 6 and then keep adding pi over 4. So I think we want intervals of pi over 12, right? So will that work? So the wavelength is pi, right? So if each one of these is pi over 12, do we have 12 of them? 1, 2, 3, 4, 5, 6, 7, 8. No, we don't. Crap. Well, we could go, this is pi over 12. Perfectly evenly spaced, if a little bit cramped. Now I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we want to start at pi over 6. Well, that's 2 pi over 12s, right? And then we want to keep adding pi over 4 to that. Now, pi over 4 is 3 pi over 12. So 1, 2, 3 from where we started. That's going to be 5 pi over 12. Right, 1, 2, 3, 4, 5, right. And 1, 2, 3 more pi over 12s will take me to 2 pi over 3. You really get to practice your fractions here and reducing, right? These are all pi over 12s, but they're reduced, right? So this would be 8 pi over 12, 9, 10, 11 pi over 12 is here. 12, 13, 14 pi over 12, which is 7 pi over 6, that's here, right? So we're going to start here at a trough where we're 0. Then here at the quarter wave point, we're at equilibrium, right? That's 1/2. Then we're at the peak, which is 1. Then at 11 pi over 12, we're at equilibrium again. And at 7 pi over 6, we're at the trough, back where we started, right? So this is a cosine curve. If you want to make it a nice smooth sinusoid. And kind of like, yeah, kind of like that. Okay. So this is our function, right? The line of equilibrium is here, y equals 1/2. And we're going to keep oscillating with the same way, right? If you want to extend the function, you could, right? Um, um, so how are we doing? Okay. Leonardo came in. Let me make a note of that. How are we doing? Yes, class is almost over. Rodriguez, nice to see you. Okay. And yeah, all right. So that's one. We got time for maybe one or two more. How about 42? Very similar sort of thing. I mean, so in general, let's draw the general case, shall we? So if you've got a situation where you have y equals, I'm just going to put in parameters here, right? D plus A times sine of B times X minus C, right? So I've got four parameters, A, B, C, and D. D is the line of equilibrium, A is the amplitude, 2 pi over B is the period, and the phase shift is C. So let me see if I can sort of fake something that looks like that, right? I don't know. This is really faking. So let's say that D is here. It's a positive Y value, and that's going to be our line of equilibrium. So I'm going to draw that as kind of a dashed line. We're oscillating around this line, right? With amplitude what? A, right? So that means we're going to go up A from the equilibrium and down A from the equilibrium, right? So that's going to be the extremes, the trough and peak positions, right? Then C is our phase shift, right? So we're going to start at equilibrium when x equals c, c minus c is 0, sine of 0 is 0, d plus 0 is d, right? So you start at equilibrium. And over here, we're going to have one wavelength down the road. So that's going to be our starting position plus 2 pi over b. And then we want to divide that into equal pieces. Let's see. So dividing it in half will take us to about here. I'm just going to eyeball it. All right, so what is this? Well, a quarter of 2 pi over b is pi over 2b, right? So this is c plus pi over 2b. This is c plus pi over b, halfway. And this is c plus 3 pi over 2b. And so we're going to be at the peak here, back at equilibrium here, at the trough here, back at equilibrium here. And I can draw in one oscillation like so, and it continues on, right? Oscillating from peak to trough and trough to peak and through equilibrium over and over and over again ad infinitum. Okay, so that's the general procedure. So a particular instance of that would be, say, 5.3, number 42, where we see y equals 1. Well, that's going to be our line of equilibrium because we're adding to that cosine. Okay, so the amplitude is 1, right? Of 3x plus pi over 2. So we see that we're going to oscillate between 0 and 2, right? 1 below the equilibrium will be 0, and 1 above the equilibrium will be 2. The period of oscillation is 2 pi over 3. So a quarter of that is pi over 6. And we've got a phase shift. So what is the phase shift? Well, it's going to be pi over 2 over 6. Sorry, over 3, right? So pi over 6. So a quarter wavelength is going to be 2 pi over 3 divided by 4 is again pi over 6. Oh, that's kind of interesting. That makes it maybe actually easier. Whoops, sorry. Off the map there, aren't we? Okay. Well, I guess we better hurry. So let's put a table of values over here. And where are we going to start? Well, we're going to start at the phase shift, pi over 6. And then we're just going to keep adding quarter wavelengths, right? Pi over 3, pi over 2. That's 3 pi over 6. So 7 pi over 6 would be 3/4. And 8 pi over 6 or 4 pi over 3 would be 1 complete wavelength. And we're going to start at a peak, right? Oh, sorry, the phase shift is negative pi over 6. I screwed that up, didn't I? I got the wrong sign. So what does that mean? Well, we start here. Oh, that's kind of unfortunate, huh? That's what you get for being in a hurry. Haste makes waste. All right. So we're going to start at pi over 6 and go quarter wavelengths, right? So that's going to be 0. I didn't really erase that all the way. So 0 pi over 6, 2 pi over 6 is pi over 3, and 3 pi over 6 is pi over 2, right? So we're going to start at a peak, which is 2, go to equilibrium, hit a trough, back to equilibrium, back to where we started at the peak. Right, and then just plot those points. It's going to look something like this. Let's say that this is negative pi over 6, which is also quarter wavelength. So I can just sort of mark off quarter wavelengths like so. And the line of equilibrium is 1. Here's 2, the peak. So we're going to start at a peak because it's a cosine curve. Hit equilibrium, hit the trough, hit equilibrium at, well, I didn't label these. This is pi over 6, pi over 3, and pi over 2. So we're back at a peak here. And this is 1 complete oscillation for this function. And it continues on in that way, right? Both to the left and to the right. All right, well, we're out of time. Any questions before we wrap this up?
Professor, I was wondering if you could post the recordings from yesterday.
Oh, yeah. I thought I had. Let me look at that. Sometimes I forget to publish things. Class video 11.2, that was yesterday. Yep. All right. Well, hearing nothing else, I will bid you. Oh, one thing is, I'll be in the Math Science Study Center between 2 and 4 today, I think are my hours. Let me double check that. It's a new thing for me. Yeah, between 2 and 4, I'm in the Math Science Study Center, which is virtual like everything else. Maybe I can leave you a link for how to get there. So maybe I'll copy that, and in here I'll add external URL. Oh, that's not what I wanted. So if I click on that, what happens? I get trying to open a Zoom meeting. It doesn't say what the address. Oh, it does up here. Okay. Uh, um, so Math Science Studies Center, 2 to 4 p.m. Tuesday, Thursday. Let's see. Yeah. Okay. Let's publish that. So see if you want to stop by and ask questions at that time. You know, my regular office hours are good too. Let me know if that doesn't work out for some reason. Okay. Ciao for now.